Welcome to the video cast on thermochemistry review. This is a review of Chapter 5 Thermochemistry, which includes several different ways of determining the heat or enthalpy of a reaction. And we'll be following along with the handout that includes these sample problems and notes. Chapter 5 in thermochemistry involves the exchange or movement of energy and physical or chemical processes that involve energy. Energy is measured in joules, which is the standard international or metric units usually used to measure energy. Calories is another unit of measure of energy that's not used very much, except in America. The first law of thermodynamics says that energy cannot be created nor destroyed. It's simply transferred. And energy is simply conserved. We learned about two different types of processes in Chapter 5. Endothermic and exothermic types of processes. Endothermic is where heat energy is absorbed or taken in by the system. Exothermic is where the system gives off energy or releases energy from the system to the surroundings. The system in this chapter and the future chapters when we talk about thermodynamics are the things that we're studying. So if there happens to be hydrochloric acid and sodium hydroxide inside of a beaker, the system would be the molecules or ions of hydrochloric acid and sodium hydroxide. The surroundings would be the beaker or the lab bench that it's sitting on or anything else around it. One of the main things we study in chemistry class is heat that's either released and given off or taken in at constant pressure. This heat at constant pressure is called enthalpy, and it's symbolized by the letter delta H. Enthalpy of certain reactions or processes can be symbolized by enthalpy diagrams. Here's an example of an enthalpy diagram. In this enthalpy diagram, you can see enthalpy is on the vertical axis, and so enthalpy increases as you go up. And you can see in this particular diagram, the reactants for the combustion of methane are on the top, and energy would be released. Notice delta H is negative 890 kilojoules as we go to the products down here. There's also an intermediate step here that you can break this up into two parts as well. One of the things that's true with enthalpy is if there was a reverse of this reaction, where we would combine carbon dioxide and water and make it into methane and oxygen, the enthalpy would be reversed. It would still take 890 kilojoules of energy, but it would be positive going from the products to the reactants. Different enthalpy diagrams to put products or reactants at the top or the bottom. It's simply necessary to be able to read the diagram and know that enthalpy increases as you go up, and that it gives you lots of information about what type of reaction or what type of process is occurring, whether energy is released from the top to the bottom or energy is gained. We're now going to take a look at 5 different ways to determine or find enthalpy of a particular process. We're going to talk about using enthalpy information from a balanced chemical equation. We're going to look at using calorimetry to find enthalpy. We'll look at using something called Hess's law. We'll look at something called using enthalpies of formation. And lastly, using bond enthalpies to determine the enthalpy of a process or of a reaction. Example number 1, information from an equation. Here's an equation. Hydrogen peroxide is decomposed to water and oxygen. Notice it's an exothermic process. 196 kilojoules of energy is given off. The question says, what is the heat symbolized by the letter Q or symbolized by the delta H since it happens to be at constant pressure when 5 grams of hydrogen peroxide decomposes? We want to know how much energy is released when 5 grams of this substance breaks apart. This equation gives us a lot of information about how much energy is released for each one of these substances. And the stoichiometric ratios actually tell us how much heat is released per 2 moles of H2O2. Notice there's a 2 in front. How much energy is released when 2 moles of water is produced, or when 1 mole of oxygen is produced. We're not given a number of moles that are decomposed. We're given a number of grams. So our first job in this problem is to convert our 5 grams to moles. So I'll take our 5 grams of H2O2. We'll put grams in a position where it's going to cancel, and moles is our new set of units. And in 1 mole of H2O2, there are 34 grams. This number comes from the formula mass on the periodic table. If I add up hydrogen, which is 1, and there's 2 of them, and oxygen, which is 16, and there's 2 of those, I'll end up with 34 total. Once I have my number of moles, now I can use my ratio on my balanced chemical equation that shows that there are 2 hydrogen peroxides for every 196 kilojoules of energy released. Since I have moles of hydrogen peroxide, I can say for every 2 moles of H2O2, 196 kilojoules of energy are released. Notice how having this thermochemical equation allowed me to write the relationship 2 to negative 196 kilojoules. When I plunk this into my calculator, 5 grams divided by 34 times a negative 196 divided by 2, I end up with negative 14.4 kilojoules. That's the amount of energy that would be released. Now it's important to be able to think of the reverse of this question too. What would you have to solve for, or how would you solve a problem if they told you that, let's say negative 28.8 kilojoules of energy was released, how much H2O2 was decomposed? Now they could ask you the moles of H2O2 that was decomposed, or they could ask you the grams of H2O2 that was decomposed, or if this question happened to be for gases, they could ask you a volume, or they could ask you a number of molecules as well. So using the mole interconversions is very important. So if you know 28 kilojoules is given off, you can use the relationship that for every 2 moles of H2O2, negative 196 kilojoules is given off, and you can figure out how many moles of H2O2 would have been decomposed. So that's information from an equation. The second method of finding enthalpy is using something called calorimetry. Now, calorimetry has 2 fairly common equations that are used at constant pressure. The first one that you'll find on your equation sheet for the AP exam is that Q, or delta H, as long as it's at constant pressure, is equal to mass times specific heat times the change in temperature. Now the textbook we're currently using uses an S in place of the specific heat, but your equation sheet, if you look at that, uses the small letter C. And I'll zoom in on this just a second. can see that the equation right here on the equation sheet for the AP exam uses Q equals mass times C, which stands for specific heat, times change in temperature. And all of these variables are defined for you over here, where you see Q is heat, C is specific heat, and T stands for temperature. The second equation that's used quite a bit is right below it. This stands for the molar heat capacity is equal to the enthalpy divided by the change in temperature. Your book uses a little bit different symbolism for molar heat capacity, but we'll use C with a small p and call it C sub p is equal to change in enthalpy, or enthalpy change divided by change in temperature. Remember that Q stands for heat, and as long as heat is at constant pressure, it also stands for enthalpy. Our first problem to solve using these equations is how much heat is needed to warm 250 grams of water from 22 degrees Celsius to 98 degrees Celsius. And it gives us the specific heat of water as 4.184 joules per gram Kelvin. Since the temperature is changing, we'll use the temperature change equation. Q is equal to mass times specific heat times change in temperature. The mass of water that we're heating is 250 grams. The specific heat of water is 4.184 joules per gram times Kelvin. And our temperature change is 22 to 98. So 98 minus 22 should give us our change in temperature. And notice they use Celsius degrees here. But remember, 1 Celsius is analogous to 1 Kelvin. And so when we find the temperature change of 76 degrees Celsius, that's the same as a change of 76 Kelvin. So we can simply put 76 Kelvin in here. Notice our kelvins cancel with our kelvins, grams with our grams, and we're left with joules as our answer. If you plunk this into your calculator, you get 7.9 times 10 to the 4th joules of energy that's needed. The second question is, what is the molar heat capacity? A lot of people get confused when they hear the word molar. Just remember, molar means per mole. How much energy per mole will it take? Well, we're told that the specific heat of water is 4.184 joules per gram times Kelvin. Now we want to know how many joules there are per mole to raise that substance 1 degree Kelvin. And so we simply have to convert from grams to moles. And if you put grams in a position where it's going to cancel, notice grams are on the bottom here, so you want to put grams on the top here. And moles is my new set of units. And since I'm working with water, I need to look up how many grams there are in a mole from the periodic table. Oxygen's 16, each hydrogen's 1. There's 18 grams in 1 mole. And if I multiply 4.184 times 18, cancel my grams, I end up with 75.2 joules per mole times Kelvin. This is called the molar heat capacity of water. Here's another calorimetry example. When a student mixes 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar NaOH in a coffee cup calorimeter, the temperature of the resultant solution increases from 21 to 27.5. Calculate the enthalpy change for the reaction, assuming the calorimeter only loses a negligible quantity of heat. The total volume of the solution is 100 milliliters. The density is 1 gram per milliliter, and the specific heat is 4.184. Now, a coffee cup calorimeter might sound kind of strange, but I'll put a picture of one up here from your textbook. You can see here's the coffee cup, and it's got a thermometer and a stirrer and a top to it. And notice that there's two styrofoam cups nested together, so not much energy is released to the atmosphere. Well, when we do this equation, or when we do this reaction, we're going to mix hydrochloric acid and NaOH. And when we do that, we're going to get water, and we're going to get some sodium chloride, and there's going to be a certain amount of heat produced. Notice that the temperature raises. If the temperature goes from 21 to 25, we can assume that the enthalpy change is going to be negative. In other words, it's going to be an exothermic process. To find this exothermic process, we can use the equation Q is equal to mass times specific heat times change in temperature. But we should put a negative sign in front of it because we know that heat is released, or it's heat produced in this particular reaction. Now, to find the mass of these substances, we can use the density that they gave us. Remember, density equals mass divided by volume. If I use the density triangle to find mass, I simply need to know that the density is 1 gram per milliliter, and my volume is 100 milliliters of solution. So there's 50 milliliters of NaOH and 50 milliliters of HCl. If I multiply those two together, I find out that I have 100 grams of solution. Putting this into my equation, heat will be equal to 100 grams times the specific heat, 4.184 joules per gram Kelvin, and my temperature change is from 21 to 27.5, which is a 6.5 Kelvin temperature change. Canceling my kelvins and my grams, I'll be able to solve for the number of joules. Notice it's negative because it's an exothermic reaction. 2.7 times 10 to the third joules of energy would be needed to have this process occur, where heat would be produced or given off, or it would be exothermic in this case. Think also in terms of what other kinds of equations could be solved using this equation. They might not only ask for heat, they might ask for what is the final temperature, or what is the initial temperature. They might ask for what is the mass of the substance if they give you Q, or heat, and a change in temperature. They also might say that there is a coffee cup calorimeter with a certain amount of water in it, and they might tell you that something is dumped into the coffee cup calorimeter, like a piece of metal or something. In this case, this piece of metal that's perhaps heated up will lose some heat, and if we assume that the coffee cup calorimeter doesn't absorb too much heat or not much escapes from it, the heat will be gained by the water. And so you can set Q equal to Q in this case, and you can say that the mass times the specific heat times the change in temperature of your metal, or your substance that you're dumping in there, is equal to the mass times specific heat times the change in temperature of your water. These types of problems are fairly common. You have to solve for one of the variables in that type of equation. That's calorimetry. That's constant pressure calorimetry. The second type of calorimetry is called bomb calorimetry. In bomb calorimetry, we use a device that has a constant volume. Now the pressure might change. But usually it's quite negligible compared to what the difference it would make in determining our enthalpy. This is a picture of a bomb calorimeter. You can see here's the actual container that has a constant volume. Put your substance in and it's ignited, and then the heat energy that's given off from this is transferred to this water. And the water's stirred up really well, and you can see that here's a thermometer to check the temperature of the change of the water temperature. Well, we'll do one problem with bomb calorimetry, a real quick one. Constant volume calorimetry. The general equation used for bomb calorimeters is that Q, or heat energy, is equal to the heat capacity of the calorimeter times the change in temperature. The heat capacity of the calorimeter either needs to be solved for or determined in some chemical reaction where there's a known amount of heat released or gained, usually released. And then the change in temperature, of course, is just the initial to the final change when something is combusted in the bomb calorimeter. And the negative sign is because heat is released in the bomb calorimeter to the water that's usually inside of it. So here's a question that involves methyl hydrazine. You can read this equation right here, and you can see that 4 grams of it is combusted. And it also tells us that this is the heat capacity of the calorimeter, and that our temperature changes from 25 to 39.5. It asks us, what is the heat of reaction for the combustion of the methyl hydrazine? And it wants to know it per mole of this as well. So if we look at the information that we're given, we're told the heat capacity of the calorimeter is 7.794 kilojoules per degree Celsius. And we're also told that our temperature changes from 25 to 39.5. And if you do subtraction, you can find out that's a change of 14.5 degrees Celsius. Degrees Celsius cancels, and there are 113 kilojoules of energy released in this particular situation. Okay, but the question asks for heat per mole of the methyl hydrazine. And since we know that 113 kilojoules are given off for every 4 grams of the methyl hydrazine, notice in the question it tells us there are 4 grams that are burned. We can take that grams and we can convert it to moles. And then we'll have our molar heat capacity for this methyl hydrazine. Whoops, this should be grams right here. Grams of the CH6N2. In 1 mole, if you add that up on the periodic table, there are 46.1 grams. The grams cancel with the grams. Divide by 4, multiply by 46, and I end up with 1.3 times 10 to the third kilojoules per mole for my heat of combustion of methyl hydrazine per mole. That takes care of calorimetry. There are 3 other ways for us to learn how to solve for enthalpy, or for the heat of a reaction. The third one is called Hess's law. Hess's law allows us to take several steps of a particular reaction, add them together in different ways, and find out the overall enthalpy for a different reaction. So in this case, we're told to calculate the enthalpy for a reaction 2 carbons plus a hydrogen yields C2H2. And we're given 3 possible reactions to use to help us come up with this reaction's enthalpy. Now the enthalpy for a lot of reactions have already been tabulated, so it's handy to be able to manipulate these equations and add or subtract them together to find out what the enthalpy for this reaction would be. So to manipulate these equations to make them work, first of all, I'll take equation 1. I'll just number these, 1, 2, 3, and I'm going to flip it around. And the reason I know to flip it around is because the thing that I want, C2H2, is a reactant in this equation, but I need it as a product here. When I switch that around, I have 2CO2 plus H2O goes to C2H2 plus 5 halves O2. But when I flip it around, my enthalpy also must change. My enthalpy now, since it was negative 122.9, now becomes positive 1299.6 kilojoules. Notice I switched the sign when I flipped the reaction. Second reaction now, I'm going to take and I'm going to multiply that one by 2. The reason I'm going to multiply it by 2 is because I've got 5 halves O2 on this side, and I'm going to need more oxygen to cancel out with that. I also know in my reaction I need 2 carbons on this side of the reaction. If I take the reaction and multiply it by 2, I have to take my enthalpy and multiply it by 2. So when I multiply this reaction by 2, it ends up having 787 kilojoules instead of the 393. Equation number 3, I'm just going to leave it. In equation number 3, hydrogen plus 1/2 oxygen goes to H2O, and the enthalpy for this reaction is negative 285.8 kilojoules. Now if I take these reactions and set them up properly, I can add them all together. When I add them together, things that are the same on the left and the right cancel out, and then I can simply take the enthalpies and add those together as well. So my 5/2 O2 go with my 5/2 O2 over here. Notice my water cancels with my water, and my carbon dioxides cancel with my carbon dioxides, and I'm left with the reaction 2C plus H2 goes to C2H2. If I add all of these enthalpies together, I end up with an overall enthalpy for this reaction of 226.8 kilojoules. Notice it's positive. The fourth way to find enthalpy for a process is to use the standard enthalpies of formation. The standard enthalpies of formation are symbolized by delta HF with a little circle. The little circle means standard conditions. Standard conditions for thermochemistry are 25 degrees Celsius, 1 atmosphere, and usually 1 mole of the substance that's created. Standard enthalpy of formation, the little F down here, means that there's a reaction that forms 1 mole of the compound from its elements with all the substances in their standard states. Of course, the most stable form of an element is defined as having a standard enthalpy of formation of 0. So, for instance, oxygen gas at 25 degrees Celsius and 1 atmosphere has an enthalpy of formation equal to 0. Because that's its most standard condition, or its most basic state. Well, the question we're here to solve says that use the value from Appendix C on page 1123 in the 10th edition to determine the enthalpy of reaction for the combustion of pentane gas to form carbon dioxide gas and liquid water. Before we do this problem, I just wanted to give a couple of examples of equations that illustrate the standard enthalpy of formation of different substances. So, for instance, if we took sodium, solid, which is at its standard conditions, and we took oxygen, gas at its standard conditions, it'll form Na2O, solid at its standard conditions. This would be an example equation of forming Na2O, and its enthalpy of formation could be determined from this. Here's a second example. Notice it's in its standard conditions, solid and gas at 25 degrees Celsius. this equation would not be an equation that would show the standard formation for KCl. Why not? Well, two reasons. First of all, potassium here is in its liquid state. And the potassium is not a liquid at 25 degrees Celsius, it's a solid. And secondly, the definition is that it forms 1 mole of the compound. And if you look here, this is 2 moles of KCl. And so this would not be an equation showing the standard enthalpy of formation of KCl. Whereas this first equation right here would be showing the standard enthalpy formation of Na2O. Let's go back to our problem for just a second, and we'll solve that one. You can use standard enthalpies of formation to determine the enthalpy of a reaction simply by using this equation. The enthalpy of a reaction is equal to the summation of the enthalpy of formations of your products and subtracting from that the summation of the enthalpy of formation of the reactants. Products minus reactants. And don't forget to multiply each one by its coefficient if there's more than one in a particular reaction. Well, in this question, they ask us to find the enthalpy of formation for the combustion of propane. Propane is C3H8. It's a gas. And we need to burn it in oxygen. And then when we burn it in oxygen, we'll get carbon dioxide and water. And we'll produce liquid water, and we'll produce gaseous carbon dioxide. Because they are in their standard states at 25 degrees Celsius. And if we balance this equation, there's one of these for every 5, for every 3, for every 4 of these. Well, if we wanted to find the enthalpy for this reaction using enthalpies of formation, we could say that the enthalpy of reaction is equal to the summation of the products, enthalpies of formation. And if you look on page 1123 in your textbook, you can find the enthalpy of formation for carbon dioxide is negative 393.5 kilojoules. Notice there are 3 of them though, so I need to multiply that by 3. I sum that together with water, and the enthalpy of formation of water is negative 285.8 kilojoules. Notice I multiplied that by 4 because there are 4 waters. And that's my products, and I'll subtract the reactants. The reactants are C3H8. Whoops, it's supposed to be a H there and an 8. Sorry about that. And so my products are propane and oxygen. So I'll sum those together. Propane, if I look in the back book, in the back of the book, has an enthalpy of formation of 103.85 kilojoules. Notice there's only one of them, so I only have to put 1 in there. And I'd add it to the enthalpy of formation of oxygen times 5, because there's 5 of them. But if I look in the back of the book, the enthalpy of formation for oxygen is 0. Why is it 0? Well, because oxygen is in standard state at 25 degrees Celsius, and it's in a gaseous state at that temperature. And so the most basic form of any element or any compound, any element at standard conditions is defined to be 0. Well, if I multiply these together, add them up, subtract negative 103.5, I end up with an enthalpy for the reaction of negative 2220 kilojoules. Notice what this tells us about the reaction, that for 1 mole of C3H8, 2,220 kilojoules of energy would be released. Think also in terms of these problems in case they gave you a different variable. They didn't ask you for the enthalpy of reaction. Perhaps they gave you the enthalpy of the reaction, but they didn't give you the enthalpy of formation of water, and they wanted you to find that. Now you might say, well, I can just look in the back of the book to find it. But on an exam, you might not be given a back of a book. And so in this case, what you simply need to do is make this be your variable, plug in the numbers that they give you for carbon dioxide and for propane in this case, and the enthalpy of reaction is given to you probably as a question in the problem. You'd solve for a different variable. So always think in terms of solving for other things. Just in this case, they gave you the enthalpy of reaction to solve for. Okay, the very last thing to solve for, or the very last way that we're going to talk about today for finding enthalpy, is using something called bond enthalpies. Now, bond enthalpies are talked about in your textbook on page 132. On page 132 of your textbook, they give a list of bond enthalpies. I'll just pull this onto the screen for a second. You can see right here is a table for average bond enthalpies. And you can see different enthalpies or different bonds have different energies that are used to break them. And we can use this energy that's put in to break bonds to determine the enthalpy of an overall reaction as well. This is a real common type of problem to be used. It says the bond enthalpy is the enthalpy change for breaking a particular bond in 1 mole of a gaseous substance. Use bond enthalpies from page 330 in your text to estimate the enthalpy of reaction for the combustion of gaseous ethane producing carbon dioxide gas and water vapor. Well, the equation for this, for ethane, is C2H6, and we're given that it's going to combust, so we have to react it with oxygen, and we're going to produce carbon dioxide and water. To balance this reaction, I'd normally have to have 2 of these, 7 of these, 4 of these, and 6 of these. But if I look back at the question, it says, use bond enthalpies to enthalpy the reaction for the combustion of gaseous ethane. Usually what's done is that we find out what the enthalpy of combustion would be, or the enthalpy of the reaction would be, if there were only 1 mole of that reactant. To make it so there's only 1 mole of this reactant, I rewrite the equation with only a 1 in front of here. That means I'd have 7.5 moles of O2, 2 carbon dioxides, and 3 waters. Now, to find the enthalpy of formation using bond enthalpies, we just use a simple equation that says the enthalpy of a reaction can be estimated by taking the bond enthalpies of the bonds that are broken and subtracting the bond enthalpies of the bonds that are formed. Bonds broken minus bonds formed. To know what kind of bonds there are, you usually have to end up drawing the Lewis dot diagrams for these substances to know what kind of bonds there are. So let's go through and do that really quick. C2H6 will look like this. Notice it has a carbon-carbon single bond, and it also has 6 carbon-hydrogen bonds. Oxygen is held together by a double bond, so notice we'll have 7 halves of the oxygen-oxygen double bonds. Carbon dioxide, remember, is held together by a couple of double bonds, so we'll have 4 carbon-oxygen double bonds. And lastly, water's Lewis dot structure looks like this, and notice we'll end up with 6 of the hydrogen-oxygen bonds. So to do the mathematics for the bonds broken minus the bonds formed, we can look on page 332 of your textbook, or in the case of a test, they'll probably give you a number of these on the test. You'd never have to memorize them. And we'd take 6 times the carbon-hydrogen bond plus 1 of the carbon-carbon single bonds plus 7 halves of the oxygen-oxygen double bond. Those would be our bonds that are broken from this side of the equation. We'd subtract from that the bonds that are formed. And there'd be 4 of the carbon-oxygen double bonds. And we'd add to that 6 of the oxygen-hydrogen bonds from the water. Now, if I look up each one of these in the textbook, and you can look them up on page 330 in the 10th edition, and you'll be able to find out what the value is for a carbon-hydrogen bond, 413, a carbon-carbon single bond, 348, an oxygen-oxygen double bond, which is 495. These are our bonds that are broken. Subtract from that the bonds formed. 4 times a carbon-oxygen double bond, 799. And 6 times an oxygen-hydrogen single bond, which is 463. These are our bonds that are formed. So bonds broken minus bonds formed will end up giving us, if I punch this into the calculator really quick, an enthalpy change of approximately negative 1,416 kilojoules. Now think in terms of this problem not only as a tool to find the enthalpy or estimate the enthalpy of a reaction, but you also could be given a different way to find the enthalpy of a reaction, or maybe be given the enthalpy of a reaction and told to find the strength of a bond. Maybe they want to know the strength of a carbon-oxygen double bond. Now you might say, well, I can just look in my textbook and find it. But what happens if it's on an exam and they only give you a carbon-hydrogen, a carbon-carbon, an oxygen-oxygen, and an oxygen-hydrogen bond strength, and they give you the overall enthalpy? Then you need to solve for this and make this a variable. So think not only in terms of using this to find an enthalpy of a reaction, but using the enthalpy and various bond strengths to find other bond strengths as well. So today we've looked at 5 different ways to determine enthalpy. The 5 ways that we looked at today: we're using bond enthalpies. We also used enthalpy of formation. We also used Hess's law. We spent a while on calorimetry. And lastly, we used information from a chemical equation that had the enthalpy in it to find enthalpies in different ways. You should be familiar with these 5 ways as a review from Chapter 5. Be prepared to do some problems on each one of these.